Today we're gonna speak about visualizing concurrency with Kotlin. So a bit about who am I. I'll be looking at my phone because that's where my speaker's notes are. The double screen doesn't work. So I'm a staff software engineer at Deliveroo, a former software architect at Get. I also spent some time as a principal infrastructure developer at Wix. And I'm an author of Hands-on Design Patterns with Kotlin book. I know that name is a bit mouthful. And so what this talk is about? Concurrency is a hot topic in the last 10 years. And the reason for that is mainly because we're hitting the limit of how fast our CPUs can get. So we add more cores to our CPUs. It means that we have more parallelism, but there's also a limit of how many cores we can add. And then there comes the concurrency. Concurrency is a way for us to optimize the resources we have, and those resources are quite limited, as I said. So the reason for my talk is that unlike some other problems, let's say design patterns, where we have UMLs and stuff, concurrency is actually quite hard to visualize. And goal of my talk is to answer questions such as, what does a coroutine looks like? And which color is your multi-reactor pattern? Before I continue, let's discuss a bit what's a concurrency and what's parallelism are. So parallelism is doing many things at the same time. So you and me are now parallel. I'm speaking, you're listening, because we are two completely separate entities. On the other hand, concurrency is doing something while you wait for something else. So our brains, for example, they are not parallel, but they are concurrent. We're switching between different tasks, creating an illusion that we do more than one thing at the same time. Like, for example, speaking on the phone while driving. You check, what actually your brain does at this moment is you check the road, then you have some piece of conversation, then you check the road again. But you're switching between different tasks, and if you're not checking the road at this moment, not good. And one of the points I would like you to take out of this talk is concurrency is basically an illusion that we create. So let's go back 10 years, where the most common paradigm for web servers was a thread per request model. In some cases, it was even a process per request model. It depended very much on which technology you worked with. And that's thread per request model is the way that web containers such as Tomcat and Web Service Search as Apache operated. By the way, that's how many ecosystems still operate today. Take Ruby on Rails, for example, which is still by default, it would spawn very limited amount of processes and very limited amount of threads. And if you're running out of them, we'll see what happens next. Why we're using this model anyway? So it has the benefit of simplicity. You get a new request. Somebody wants to see cats on your site, for example. And so the web server fetches a new thread from the thread pool. Hopefully it doesn't create it on the fly. And then everything from going to the database up until rendering this fancy HTML page, everything happens on the same thread. There are even entire ecosystems that I'll build upon that concept. Take Hibernate or Spring MVC, for example, which are all built on the concept that everything you do with a request is still on the same thread. So it's very easy to use, but it has a major flaw. What happens if you don't have free threads? And here we come to the C10K problem. You may have heard of it. And the problem statement is as follows. How can we handle 10,000 concurrent connections on a single machine? And this problem is older than you think. It's about 20 years ago. It's not that new. And but why is this even a problem anyway? Like, if you have 10,000 concurrent connections, let's create 10,000 threads. What's the problem with that? So creating an OS thread has an overhead of about 1 megabyte of RAM, and that's even when your thread is idle. So you just created a thread, it still doesn't do anything. It's already 1 megabyte of RAM. And you created a thread to serve this request, so it probably will create some data structures and memory, so it will grow larger and larger. And while on modern machine, you can imagine you can create 10,000 threads. What about 100,000? Still probably no. Like, modern machines are about 16 gigabytes of RAM, 32 gigabytes of RAM. It's still not enough. And that's even before we start to discuss something like thread context switching, which may also become very, very expensive the more threads you have. So this talk is visualizing, so let's visualize. Yeah, I plan to switch more beautifully, but yeah. And I'll restart it. So let's see what it actually looks like running out of threads. Colors on the right side in the request queue are how long the request waits for being served. And on the left is our thread pool. So for example, average machine has, let's assume, 8 cores. So we have 8 threads deployed on our thread pool. And they start serving those requests. But notice that the more requests they are, the more angry red they get. And those are your angry users now. With a thread per request model, you're hitting your limits much earlier than you'll reach 10,000 concurrent connections. So this is a bit interactive. You can later on see what happens if you decrease the number of threads. So you'll see that the queue, request queue grows only faster. And for example, if I simulate more favorable for me situation, like let's say what happens when I have only 6 requests per second and I have enough threads, then you'll see that my request queue will decrease to 0. But as we've seen, this is not a model that can easily scale. So what does scale? So different languages, runtimes, and frameworks solve this problem very differently. NodeJS, for example, is known to run an event loop on a single thread, actually. And then every request becomes an event on this event loop, which is served as fast as possible. But it doesn't grow any more threads. It uses only one thread. And then Erlang, for example, uses actors and messages. And Kotlin and Go have coroutines and goroutines. In this talk, I focus on the later two. So we will speak mainly about coroutines and goroutines model. So what coroutines are? They are known as lightweight threads, or sometimes, if you're old enough, or if you're young enough, it really depends. You'll know it as green threads. So green threads were back in Java around 95, I think, and then they disappeared, and then now we're speaking about green threads again. Just a second, lost my notes. So we have those lightweight threads, and every computation within coroutine is put within continuation. You can think of continuation as a simple state machine or a function with callback. It really depends from which language you come. Coroutines can be suspended. If it awaits for an input from an outside world, it gets suspended, and then another coroutine can run. So if you're waiting for a result from a database, if you're waiting to fetch an image over the network, another coroutine can reuse the resources available. And that's actually the definition of concurrency. So I can do something while I wait for something else. So how does that work under the hood? Let's look at the following function, which downloads an image. Note that there is a keyword. It's should be pretty straightforward, no matter from which language you come, if it's Python, Java, JavaScript, or something else. But there is one keyword that I need to explain. It's the suspend keyword. So suspend keyword is a keyword that is very important to the compiler. It's not important to the programmer, but we'll see why it's so important. Suspending keyword means that this function should run within a coroutine. All functions that this function invokes, and there are 4 of them, are suspending except println. Println is a system function, and no, it's a presentation, and I'm mirrored, sorry. So I'll try to explain what's going on here. So we have this download image, which gets a string. Then it creates a URL based on this string, probably, I don't know, concatenates something. Then it prints the results. Then it goes and fetch the URL, the bits and bytes of this URL, prints the size of the image. Then it saves the image, probably writes it to disk, and prints done. That's what it does. Now let's see what the compiler does. So every time it sees a call to another suspending function within a suspending function, it breaks the original function into 2. So before and after. First, it sees that the create URL is a suspending function, so it will break it into 2. Then it will see that fetch image is also a suspending function. It again repeats the process. Again, it's repeated for the save image. And again, it's repeated for the last part, which comes after the save image. So the compiler has broken our function behind the scenes into 4 smaller pieces. And each time one of these functions returns results, as you can see, it passes its results to the next function. So it's pretty similar to callbacks. But why is that even important? Like, why do we care? Let's see the following example. Let's say we call this function out twice, once with a cat and once with a dog. And then compiler does what compiler does, meaning breaking the same functions. Again, we have functions for cat, functions for dog. But now, what happens at runtime? Let's see. So breaking the code into separate functions allows coroutines to interleave. It's especially important when the code they invoke involves some kind of I/O. And those are functions, agree with me, that they are doing some I/O, like fetching the image over the internet. So while your function waits for the results, every piece of this is a continuation. While this continuation waits for results, another continuation can run. And if we do this again, we'll see a different order because it's not the order within will be preserved, meaning that you won't ever have a situation when dog continuation prints done before you fetch the dog image. But there for sure may be a situation where first all the cat continuations are being run and then all the dog continuations are being run. So coroutines make everything better, and let's see shortly how we can make use of them. I given here examples in both Go and Kotlin in case somebody is more familiar with Go, which is also a concurrent language. And I'll go shortly over those examples. So this code, first of all, it prints numbers from 0 to 100,000. And since we are running this code from the main function, in both cases, we need somehow to tell the runtime to wait for all the coroutines to finish. Otherwise, they may finish after the program has exited, and then we don't see any results. So in Kotlin, we use run blocking for that. So that will tell our main function, wait for all the coroutines which are inside. Then we're using repeat, which basically like saying, generate me 100,000 numbers. And then launch is the one that launches a coroutine. So each number will be printed in a separate coroutine. Same goes for Go. Go is a bit more complicated because for waiting on the main thread, we'll need to use something called wait group. And then the size of the wait group is also 100,000. And for each number, we again run a coroutine, and this coroutine has to tell explicitly that, yeah, I printed this number, you can continue. And we go again. Now, I hope that was, I explained the idea, because I must tell you that I lied to you a bit. And for those two pieces of code are not actually equivalent. With Kotlin, and the way I run this example, it will be a bit different because by default, when run from a main function, it will use only the main thread. So it will run only on one thread. To actually run it on all available threads, so like Go does by default, we need to use the dispatcher's default, which is a thread pool. Usually you won't need to do that, but since my case is quite convoluted, I had to do that. And after saying that, let's see what we get. Yeah. So the columns are the threads of the dispatcher. So here I have 8 cores again on my machine, and that's the reason I have 8 threads. Every green bar is a single coroutine that I am executing. Notice that although all the coroutines are the same, they are basically doing exactly the same work, they are not spread evenly. So some threads will finish before, some threads will finish after, and that doesn't even depend on how much work they got. But definitely some threads get more work than others. That's something to keep in mind. And by the way, Go uses exactly the same mechanism. So it also spreads the goroutines across all available CPUs. So I hope that helped to clear up a bit confusion about coroutines. And how am I doing on time? What, 20 minutes? I don't have my... OK, cool. So a short summary. Coroutines are broken into smaller tasks called continuations. Continuations are executed on a thread pool. They aren't spread evenly across CPU cores. And this pattern has actually a name. It's called multi-reactor. So if you're running all your small tasks on a single thread, it's event loop. That's what NodeJS uses. And if you manage to find a way to spread it across multiple threads, then it's called multi-reactor. I think it was first used by a framework in Java called Vert.x, which uses this pattern for high concurrency. And yeah, as I said, this allows for high throughput of small tasks, and Go uses exactly the same model under the hood. So our next part is more practical. And say you want to fetch all images from a certain internet page, like you just love lolcats, and you want to go to this homepage and fetch all the images of those cats. So what will you need to do? First, you need to fetch the HTML. Then you're going to parse it to find all the image tags. Then you download each image, and probably you want to save each image to a disk. And of course, we don't want to do that sequentially. Say I have 1,000 images. Every image downloads like 10 seconds. I would like to use as much resources as possible to finish this task as quickly as possible. So fetching and parsing is something which is done only once, or relatively fewer times than fetching the actual images. But there can be many images on the same page, and that's the part that we want to make as concurrent as possible. So we'd like to distribute this work. In Kotlin, we can use a function called produce, which starts a coroutine and binds it to a channel for that. And then what we will do, we have this function called scrap, which gets a URL which I want to fetch. And then we call produce. Produce is a function that starts a coroutine and also returns a channel. So as you can or maybe cannot see on this projector, it returns something called receive channel. And then inside this coroutine, we fetch the HTML, parse all the links, and then we start sending those links on the channel. So let's understand what channels are. So channels are a way of communicating between different coroutines. So if you want to coroutine to continuously process some kind of data, you create a channel for that. This part is the function we've seen earlier, the scrap. And let's say I start two coroutines, each of which should fetch the images. Now, both of those coroutines listen to the same channel. And to get the messages on the channel, we can use a for loop. That's what we usually use on arrays, but we can use it in Kotlin also on channels. And every time we push a new message, we send a new message over the channel, only one of the coroutines will win. So they will try both to get this message, but the message will arrive only to one coroutine. And if I have 8 coroutines, it will be exactly the same. So only one wins every time. So let's see. First arrives here, second arrives here, third arrives here, and so on. And then inside the for loop, you basically got your next message, and you can, in this case, fetch the actual image. So for those coming from JVM languages, channel are blocking queue, but they are not blocking. They, instead of blocking a thread, they suspend the coroutine. a second, finding my notes. What happens though if, let's say, have two coroutines, but they are both busy? So one says, no, I cannot do this work. Another says, I cannot do this work, and there are no more coroutines. So what will happen is that the scraping coroutine now, the one that sends those messages, will be suspended. It will wait until one of the coroutines will get released. And then again, the process repeats itself, so it will be like that. So let's go to the next part and discuss a bit storing of those images. So up until now, static electricity. Up until now, we only fetch those images, but they are still in our memory. Now we need to store them to disk. Of course, we can decide that each coroutine just writes the image it got by itself. But that's not really a clean code. It's not a good separation of concerns, right? So it would be more efficient if only one coroutine, a special one, would do the save to disk. So we'll create a new coroutine. And if previously we used a producer, which returned us a received channel, now we use another constructor, which is called actor, and it returns us a send channel. So actor is a more simple constructor than a usual an actor like in Akka or in other languages. It only has one channel, and in this case, it's an incoming channel. And then we can do something very similar to what we did before. So this channel is the channel of objects and not like it was previously a channel of strings, but we do for loop on the channel, and each time we get a new message, we just process it. So last and most risky. Okay, so the reason this is risky is because this is done in real time, actually. Behind the scenes, I'm running a Kotlin server, which actually sends the messages. And each time the message is being sent, I also replicate it and send it to JavaScript UI via WebSocket. So this is all the real time. You can also, if you get the examples, you can also click the nodes, and you can see what each node actually does. So those are our scrapers, which just distribute the images, distribute the links. And then each of those nodes are the ones that are fetching the links. And you probably cannot see it, but those lines say that we have one incoming channel and one outgoing channel. So one channel, you send the links you want to download, and then when you finish downloading the links, you send the newly created message saying, that's the byte array of this image, that's its name, please go and save it. And the last part is actually saving the image. So we wait for each time for a new message. And each time a new message is received, we save it to disk. So again, as a lot of things in computer science, this is LI. So I would like, I hope it works. Yeah. And the reason it was LI is from the previous diagram, it may have seemed that each coroutine has an incoming channel and an outbound channel, but this is not the case. In our program, we have only two channels. So we have one channel for the links, which all coroutines are listening to, and we have one channel for the saved objects that, again, all coroutines are sending to the same channel, and there's only one coroutine that saves those messages. So, to summarize, seeing is believing, as hopefully I convinced you. And now you've seen a coroutine and a multi-reactor and fan in and fan out. One last thing I forgot to mention is that as there is a name for design pattern called multi-reactor, this also has a name. And to explain that, I'll need to go to the previous example because it will be clearer. So it's called fan in and fan out. So the top part is actually fan out. So you have a bunch of messages which you spread across different coroutines in this case, or actors. And the lower part is called fan in. So we got all those messages, and now we need to collect the results. So you may know it as divide and conquer. You may know it as map reduce. It's all the same. In case of concurrency, it's often called fan in and fan out. So now you also see fan in and fan out. So seeing is believing, concurrency is an illusion. Goroutines are just coroutines, but it's important to understand how they work. And I hope I also convinced you that concurrency with Kotlin is pretty awesome. If you like this talk, I also wrote a book, as I mentioned, which covers also those patterns. And if you like to stay in touch, those are my social links, and also the link to the repository, which you can just run on your laptop to see the different animations and stuff. I warn you, the JavaScript code is horrible. It's plain. I decided not to use, I use a specific library to render the actual graphs, but I don't use anything fancy, so it's plain old JavaScript which with a lot of ifs. So yeah, thank you very much. If you have questions, just catch me after this session and I'll happily answer them. Thank you.